So today we're going to move on to our second lesson in exponential and logarithmic functions. We're going to look specifically at properties of exponential functions, primarily what their graphs look like. So here's our objectives. The first one is to be able to generate the parent function graph for any exponential function. And then the second part is to apply transformations to the graph of the family of exponential functions. So this lesson will sound familiar because we did the same thing with linear functions and quadratic functions. So today we're going to look and see what does this look like for exponential functions. All right, so remember the parent family is the most simple form of a function with no transformations. So we want to figure out what would that look like for an exponential function and what would its graph look like. So let's take an example here. And it says a unique parent function exists for each base value b, right? So remember, b is the growth or decay factor. So whatever that number is, it's going to have its own unique parent function. So let's look at y equals 2 to the x power and see what would that graph look like. Well, we can certainly create a chart of x and y values and plot those and see what it looks like. So let's do that. So if we take 2 and raise it to the negative third power, we get 1/8. Now, how does that happen? Remember, raising something to a negative power, we can make positive by putting it as 1 over that power or base and exponent, but this time it changes to a positive. So that gives us 1/8, 1/4, 1/2. Anything raised to the 0 power is 1, and then the rest is pretty straightforward, right? 2 to the first power is 2, 2 squared is 4, 2 to the third power is 8. All right, let's put those points on the graph here. Well, actually, we're not going to put all these points on the graph. What we are going to put is a critical point, which is the y-intercept. So remember, the y-intercept will always be 0, 1. The y value will be 1 because the y-intercept by definition is where x is equal to 0. And anything raised to the 0 power is 1. So notice this point right here will occur no matter what the base value or b value is. And then let's find the second point. Well, let's use x equals 1 because it's very easy to take our growth factor and raise it to the first power. So that will give us this point here, right? And now we can sketch the curve, okay? So to figure out what the parent function looks like, the graph of it, we really just need these 2 points, 0, 1, which will be the y-intercept no matter what the b value is, and then a second point when x equals 1, that will depend on what the b value is. So to sketch this, that's all we need is those 2 points. Now there's one other important element to the graph of exponential functions, and that's something called a horizontal asymptote. Now an asymptote is, think of it as a boundary value that the graph will become very close to, but never actually equal, okay? So the asymptote in this case is going to be the x-axis. And you notice as we go to more and more negative values for x, the y value becomes smaller and smaller, okay? And it will get very close to 0, but never actually equals 0. You can see how the graph, the line of the graph gets closer to that, but doesn't actually touch it. Here's another way to think about it. If I ask you to go half the distance to a wall in a room, say in our classroom, each time, and then just keep doing that over and over. But the rule is you can only go half the distance. Will you ever actually touch the wall? And if you think about it, you'll get very, very close to the wall, but if you can still only go half the remaining distance each time, you'll never actually touch it. Okay, so in that case, that wall would represent the horizontal asymptote. So let's define it this way. An asymptote is a line that a graph approaches but never touches. Think of it as a boundary value. All right, so that's really all we need to be able to see what the parent function looks like. Let's look at another example real quick here, right? This time our growth factor B is 3. So we're going to plot the y-intercept. So 3 to the 0 power is 1. And then we're going to plot the value when x is equal to 1. So 3 to the first power is, of course, 3. And our horizontal asymptote. And now we can sketch in the curve. Okay, so very easy, very quick to sketch what the parent function looks like. 2 points, draw on the asymptote, and then sketch in the curve. Let's do one more. Okay, so notice as we get larger values for b, right, then that shape of the exponential curve will get steeper and steeper. All right, what if it's decay? What if our growth factor is actually a decay factor less than 1, 1/2 in this case? So again, we could plot all these points, but rather than do that, we're going to use the same method, right? The intercept will still be 0, 1. And this time, if we take 1/2 and raise it to the first power, we get 1/2. Right? So we'll get a point here. Now, remember the curve is going to look a little different. It's going to start at very high values and then approach the asymptote as we get to more positive values of x. So that's what it would look like. And of course, we have our horizontal asymptote on the x-axis. Okay, one more example here. 1/4. There we go, a decay function, sketch of the parent version of the decay function. All right, now let's apply this to the family of exponential functions. Okay, this is what's going to look familiar. We looked again at these transformations for linear functions, and we did it for quadratic functions. Now we're going to do it for exponential functions. So notice I've added an a value, an h value, and a k value. So what do these do? Well, they do the same thing as they did with other functions. So if a is greater than 1, we have a stretch. If a is less than 1, we have a shrink. If a is negative, it's going to create a reflection of the function. What about h? H, because of the negative sign in front of it, we're going to have to think kind of opposite. So if h is positive, then we're going to go to the left. We're going to shift the whole function to the left if it's negative to the right. And then our k value is our vertical shift, positive up, negative down. All right, so let's look at some examples of these. So here we have a reflection. So the parent function is just y equals 2 to the x. Let's sketch that really quick here. So that will be in black on our graph. And then what will the negative do? The negative gives us a reflection. So we're going to take these 2 points and reflect them around the x-axis. So positive 1 becomes negative 1. Positive 2 becomes negative 2. Now, will the asymptote move? Well, if it's just reflected and it's sitting right on the x-axis, then the answer is no, it's going to stay where it's at. So now we can sketch in our reflected function. Okay, there's a reflection. Let's look at if our a value is greater than 1, which is a stretch. So again, we put the parent function in. Do this pretty quick here. And then a stretch, remember, is we take the y values and multiply them by the a value. So the 1 becomes 2. The 2 becomes 4. The asymptote, since it's at 0, if we multiply it by 2, we still have 0. So the asymptote will not move, and we can sketch in our stretch. How about if it's a shrink? If a is 1/2, well, we're going to do the same thing. Take our original points and multiply them by 1/2. So 1 becomes 1/2, 2 becomes 1, and we can sketch in our shrink. So similar to what we saw with quadratic functions and parabolas, it's like stretching or squashing the values. All right, horizontal translation. Y equals 2 raised to the x minus 3 power. So our h value is a -3. Let's put our parent function in here. So now we're going to, since it's negative, we're going to move it in the opposite direction. So we're going to go 3 to the right for both of these points. The horizontal asymptote, you could think of it as sliding along the x-axis, but it's not going to really change its location or appearance. So that stays. And now we can sketch in the horizontally translated function. How about a vertical translation? K equals -4. So we're going to go down 4 with each of those 2 points. Now, what happens to the horizontal asymptote? In this case, it is going to shift with the other points, right? So we're going to move the asymptote down 4 also, and that helps us to be able to sketch in the new function that has a vertical translation. All right, so here's a summary, right? I'm just going to fill this in quickly here. You've had this summary before. Everything pretty much is the same. The only difference is the family of functions up above. But A, H, and K all do the same transformations. All right, how would we sketch this? We got a little practice. Y equals 2 raised to the x plus 3. So start with the parent function. Identify the transformation, right? It's a vertical. So we would move everything up 3, including the asymptote. That's the only time it moves is when we have a vertical transformation, and then sketch in the new function. Let's try another one. Y equals 2x to the minus 3, or 2 raised to the x minus 3. So parent function. This time it's 3 to the right with a horizontal translation. And the asymptote stays in the same place. All right, we have a stretch now, right? A is greater than 1, so a factor of 3. 1 becomes 3, 2 becomes 6, and we sketch it in. Notice the asymptote remains on the x-axis. And a -4, what would that do? Well, we have 2 things going on. We have a stretch, but it's also negative, so we're going to have a reflection. So let's do that. Let's do the reflection first. So the 1 becomes -1, and then multiply that by 4, we get a -4. The 2 becomes -2, multiply that by 4, we get -8. Asymptote stays the same, and there's our transform function. All right, one more. Y equals 2 raised to the x plus 3 minus 2. So again, we've got a couple things going on here. Here's our parent function. Horizontal, we're going to move 3 to the left and down 2. So let's do that. 3 to the left, down 2, 3 to the left, down 2. And this time the asymptote also needs to move down 2. So here's our new exponential function. Okay, let's see, I'm going to skip through these other examples. There we go. So we know what the parent function looks like. We just need those 2 points, right? The y-intercept at 0, 1, and the value when x is equal to 1 to create the sketch of the parent function. And then we apply the transformations. What does A do? What does H do? What does K do? Things that we've seen before with other functions. All right, that's it.